Now we are going to start with another property of 14 group, that is reaction with halogens. We see that whenever element react with halogens, they form their respective halides. This is already known to you. So likewise, this group members like the carbon family also form the halides of molecular formula MX4 and MX2. So that means they form two types of halides. One, they form dihalides, right? And they also form tetrahalides. This you have seen that see, the formula is X4, that means tetrahalide. When it is X2, it is dihalide. So first we'll talk about the tetrahalides. All tetrahalides like CCl4, I'll write here, like CCl4, SiCl4, germanium tetrachloride, tin tetrachloride, chloride. So we have seen that all the tetrahalides, what kind of bonding they are having? Covalent. This we have already discussed, that whenever they will make use of their +4 oxidation state, the bonding will be covalent. This we did when we were discussing about the general outline of the chemical properties. So again the same thing here, all they are making use of +4 oxidation state. So the bonding which is to be there is covalent. But if we talk about SnF4 and PbF4, because there is a large electronegativity difference, so therefore the bond formed by tin and lead, particularly with fluorine, is ionic in nature. This you need to remember. And what is the reason? Because whenever there is a large electronegativity difference, we know that the bond formed is ionic. So that kind of difference is seen in this when they combine with fluorine, tin with fluorine and lead with fluorine. Therefore, the particular bonding is ionic. Otherwise, with all the halogens, whenever they are forming halides, tetrahalides, that is covalent. Now talking about their stability, that whether they are stable or not, like when we heat them, do they easily break or do they break with difficulty? So we have seen that the stability and the ionic character decrease down the group. That means the thermal stability is actually decreasing down the group with increase in atomic number and size of halogen atom. We have seen that like PbCl4 and PbBr4. So that means like if we are talking about the same chloride, like if I take only lead and I say that I am talking about lead fluoride, I am talking about lead chloride, tetrachloride, lead tetrabromide and lead tetraiodide. So what we have seen that like as we are moving down, then the stability is decreasing, like I am taking the same element but I am changing the halogen. So when the mass of the halogen is increasing, the atomic number is increasing. So we see that the thermal stability is actually decreasing. And you know that we don't, this compound, that is the lead tetraiodide, is unknown. It doesn't exist. And you know that what is the reason? The reason is this, that lead in +4 oxidation state is powerful oxidizing agent and iodide is powerful reducing agent. That is the reason that PbI4 does not exist in nature. Now if we talk about their dihalides, so dihalides, that means of formula MX2, that is shown only by germanium, tin and lead. This is obviously clear because as we are moving in this, the oxidation state is +2. And you know that as we move down, the +2 oxidation state becomes stable due to inert pair effect, right? So obviously because they can only show the +2 oxidation state, their +2 oxidation state is stable. So that is why dihalides is only seen for these elements, that is germanium, tin and lead, like this. And if we talk about the stability, we know that for the heavier element, +2 oxidation state is much more stable due to inert pair effect, and lead is that element which is at the bottom, that is the heaviest of all. So obviously if we talk about dihalides, this is going to be more stable, this will be comparatively less stable and this will be least stable. And carbon and silicon, I have already mentioned that they do not form dihalides because their +2 oxidation state is not stable. The reason again that it is stable for these due to inert pair effect, but it is not stable for carbon and silicon. Now there are few important questions which is being asked, often asked in the paper related to this topic, that is CCl4 can't be hydrolyzed with water, carbon tetrachloride can't be hydrolyzed, but if we talk about the other halides, like elements of this group forming tetrahalides, like if I talk about SiCl4, germanium tetrachloride, lead tetrachloride, they easily get hydrolyzed. This is an important question which have been asked in the paper. And one more thing, you know that the compounds of this family are electron precise. That means they are not electron rich, they are not electron deficient, they are electron precise. That means they have that much number of electrons that is required to attain a stability. So coming to this point, that why CCl4 can't be hydrolyzed. As we know, carbon is very small and it is lacking d orbital, no d orbital is there, and it is already holding 4 chlorines. So because due to small size and lack of d orbital, it cannot hold more water molecules. That is the reason it can't be hydrolyzed. But if we will talk about the other halides, like if we talk about SiCl4, it can be easily hydrolyzed. Now I will show you that how this hydrolysis take place. See, let us say this is silicon holding 4 chlorines. This is what is the formula for silicon tetrahalide, and the structure is this because it is sp3 hybridized. Now, if I react it with water, we know that water has 2 lone pairs, right? I will just make an open structure. It is like this. So what it will do when it will get hydrolyzed, it will lend this lone pair to silicon and link by a coordinate bond like this. This remain as such. This is an intermediate actually, and it get linked like this, right? Then what happened, there will be, because this is an intermediate and it is unstable, it need to convert into a stable compound. So how it will convert? This HCl will be liberated, and what will we left with? Si, this Cl again remains same, this Cl same, and this Cl is being removed. Now we have bond, instead of Cl we have OH. Likewise, one by one each Cl will get removed along with H. How? So that means for removing 3 Cl, we need to add 3 water molecules. So when we will add 3 water molecules, there will be this thing, elimination of 3 HCl. 3 HCl. Then giving rise to silicon will be like this, Cl, all the Cl will replace by OH group because we have added 3 water. So it will become OH, OH and OH. This is what I have written in the formula, that all Cl will get replaced by an OH group. So how? It will occur step by step. It will make a bond with water, removal of HCl will take place, and there it will create one bond, that is with OH. Likewise, all the Cl will be replaced by an OH group along with the elimination of each HCl molecule as a result of adding 1 water molecule. So you need to add more 3 water molecules and more 3 HCl will be liberated. So this is actually seen in silicon tetrachloride and rest of the chlorides, but it is not, or the halides also, but it is not seen in CCl4. The reason because it is small in size, cannot hold the bigger water molecules with it. So therefore it cannot be hydrolyzed. One more question which you are often asked. Carbon can't form complexes, but the other members can form complexes. The same reason, too small, lack of d orbital, so it cannot accommodate, it cannot extend its coordination number beyond 4, right? Because its group oxidation state is +4, it cannot make it 6 or 7. It has to be, it needs to stick to only +4. So that is the reason it cannot form complexes, right? So this is all about the reaction with halides. I think you got it, that when they react with halogens, they form their respective halides, tetrahalides, dihalides. Tetrahalide covalent, dihalide again, it is seen only by germanium, tin and lead, and you know the stability, and here also you know the stability. And keep in mind, PbI4 does not exist, it is unknown, because Pb is a strong oxidizing agent, and iodine with I negative is a strong reducing agent. And the important question, CCl4 cannot be hydrolyzed, but rest of the halides can be hydrolyzed. You are aware of the reason, that why, and how you are going to show the hydrolysis, you know, also know that also. And why carbon cannot form complexes, this also we have discussed. So this is all about the chemical properties of the fluorine group, that is the carbon family.